So my name is Sergio Saez. I'm from the Universidad Politecnica de Valencia, and I'm going to present a new design of the real-time utilities presented by Wellens and Barnes in order to adapt these utilities to multiprocessor in general. So the idea is to present the system model, then review the real-time utilities, to review some drawbacks in order to implement some multiprocessor scheduling approaches, and then to propose an adaptation and a redesign to implement support for multiprocessor and other type of scheduling, and at the end, very briefly, an introduction to a real-time code generation tool in order to test this kind of things. So, first, the system model. Okay, the system model is the typical one, a task that's composed of an infinite number of jobs that are activated with a given pattern, periodic, aperiodic, or sporadic, and each job can be a single-step job, that is the common one, that performs some code, executes some code, or could be a more complex job that have different steps in order to achieve some kind of goal, some maybe reduce release jitters or output jitters, and this kind of tasks with multiple steps are called this kind of tasks, initial, mandatory, and final tasks. We want to support this kind of jobs also. And the step is the normal code that has the scheduling attributes, priority, CPU, relative deadline, and so on. And also we want to support some kind of handlers in order to detect different situations like miss of a deadline or maybe a cost overrun, that was always supporting real-time utilities. So in multiprocessor scheduling, as the previous talk explained, there are several approaches to schedule the tasks. The global scheduling that allows the tasks or the jobs to migrate to one CPU to another freely at any instant, depending on the real-time operating system scheduler. There are the other approach is the task partitioning. All jobs execute all in the same CPU. Okay, the task is allocated to a single CPU. There are intermediate possibility that is job partitioning, that each activation executes in a different CPU, but they are not allowed the migrations. And different approach that is a mixed approach, that is task splitting, that there are task partitioning, but there are some tasks that are forced to migrate from one CPU to another at specific times after some system clock delay or some execution time delay. So we want to analyze this kind of, to support this kind of multiprocessor approaches, and the new ADA 2012 is going to incorporate some support, some explicit support to control the CPU affinity, and as said before, the pragma to specific the initial CPU of a task, and some dispatching domains that restrict the global scheduling to a subset of the platform processors, and also some procedures that allow to change the CPU of a task or of a job. With this support, we want to help the programmer to implement the real-time behavior. Okay, there are part of the design, that is design of temporal requirements, functional code implementation and analysis. After that, we analyze the code and extract some information from the scalability analysis, priorities, CPUs, task splits, and so on. And we want to help to implement the above mentioned scheduling approaches and support this real-time behavior in the new real-time utilities. Okay, implementing all the stuff with offsets, priorities, deadlines, CPU affinities, migrations, and so on. The goals of our work is to offer a new real-time utilities that support this new these scheduling approaches in multiprocessors, and also to implement automatically the schedulability code, taking the information from the schedulability analysis and the real-time requirements. So, a brief review to real-time utilities presented by Williams and Barnes are based on 4 components. That is the first one, the real-time task, that is the task itself, the task state that implements the functional code, and also the release mechanism that allows to activate a task, a job, periodic or sporadic. So a brief review to these components. The first one is the control, the real-time task, that is the control flow of a task that implements the main initialization and the main loop, and it interacts with the state and the release mechanism to implement all the stuff. There are some minor drawbacks of this real-time task, that is that even handlers are hard code the code to be executed, but even handlers are hard code in the task. We will see later this minor drawback. The next component is the task state that implements the functional code of the task, initialization and the code to be executed in each activation, but also offers the code of the handlers for cost overrun or deadline miss, the things to be executed if this event happens. But the problem is that also you need to program in this task state all the initialization of scheduling attributes, CPU, priority, relative deadlines, and so on. And if you want to make some more elaborate scheduling approach as task splitting, all that stuff should be implemented here in the state code, in the code of the user. So, and finally, the release mechanism that allows to activate the job with different patterns, periodic, sporadic, aperiodic, and so on, and also helps to detect and to perform the notification of 2 events, deadline miss and cost overrun. The problem is that if we want to add a new event, the number of release mechanisms have to double. Okay, this is the current ones that they are periodic with deadline miss, periodic with overrun detection, periodic with deadline miss and overrun detection. If we want a new event to be handled, we need to double the number of release mechanisms. So this is an example from the previous paper, and here you see how to declare your state. You have to initialize the code, and then you configure the simple task. This is a simple task. The problem is that initialize has to initialize the scheduling attributes, deadlines, CPU affinity, and so on. And if you want to perform a task split, you need to implement in the code procedure. So we want to avoid this kind of behavior and also to support multiprocessor scheduling. So which are the requirements of multiprocessor scheduling, or in general more complex scheduling? So deadline-based scheduling requires to set the absolute deadline just after the task release. So this, with the real-time utilities currently, this is not possible. We want to support this set deadline on release. We want also to allow this kind of task with several steps that only requires to allow offsets. This type of task are decomposing subtasks, initial part, mandatory part, and final part, and only need offset for implementing that, but this is not supported right now, the offsets. Task partitioning only requires to set the CPU with a pragma or with a procedure during the initialization, but job partitioning requires to set the initial CPU and after the job execution to specify the next procedure to be executed. And this needs to be performed in a protected code related to the release mechanism. That right now is not possible. And finally, the task split that the task splitting technique that needs a lot of stuff, needs the set the CPU, set a handler at the beginning of the job, to program a temporal event that executes some protected code to change the CPU, and after the execution of the job, you need to reset your scheduling attributes to the original ones. So all that stuff needs to be incorporated in the real-time utilities. So we need to redesign these real-time utilities to support more than one set of scheduling attributes for a task. We need more events to be triggered after a CPU or a system clock delay. And we also need to execute things at the beginning of a job or at the end of that job. So the idea is to provide these new real-time utilities. And the first thing is to decompose the task state in three different components. The first one is the task state that is only the functional code of the task, that has this implemented by the user. The task attributes that stores all the attributes of a task or of a job or an event, including that allows a task to have multiple scheduling attributes or associate attributes with a scheduling event, or implement scheduling plans. And these scheduling attributes stores all the stuff: priority, CPU, deadlines, offset, etc. And finally, the task sched that contains the scheduling code that is associated with the task, and that implements all the stuff to perform all these scheduling approaches. The idea is to this last component be generated from the system requirements as scalability analysis report automatically. So this is the relation. We have here the procedures to be implemented by the user, and these procedures, that is scheduling related procedures, that are generated from the system requirements. The initialization, change task attributes, change job attributes and a given instant, mode change handlers, and so on. And this task scheduling code has one or more scheduling attributes with offset, deadline, execution time, priority, CPU affinity, and so on. The second part is to support more events to allow to perform task splitting and job partitioning. So the idea is to detach the event management from the release mechanism, and we propose two new components, that is control objects and control events. And the control objects determine when an event is executed or is dispatched, can be executed on job release, or after a CPU clock delay, or after a system clock delay, or on completion. We have here some examples, the scaling techniques that requires this kind of releases, of event execution. And also in another part is the control event that determines which actions should be executed on an event dispatch. This determines when, and this determines what have to be done. Here we have a diagram that relates the control objects, the four control objects, with system clocks or CPU clocks, and on-release dispatch and completion dispatch. And this is the possible control events to perform task splits, system clock sched evening, or CPU clock sched event, or to detect deadline miss or cost overrun. Oops. This is an example of task split technique. Can declare use this kind of event, the scheduling system clock scheduling event. That this is a dispatch. This says that when the event is dispatched, we execute adjust our job attributes, and this procedure, this function offers set when this event have to be triggered. Okay, in the task initialization, you declare, initialize the scheduling attributes of the task split, the offset to perform the split, and the target CPU. Declares the control event associated with these scheduling attributes, and initially declares a new control object that uses this control event and associated with the release mechanism, and registers the control event in the release mechanism of the task. 2.1. Okay. Release mechanism have been simplified because we need only two kind of release mechanisms. Okay, two kind per activation pattern. So the periodic release mechanism only needs two kind of objects. The simple one that does not require anything, but only offsets. And the new one that the release mechanism with control objects that allows to register a variable number of control objects to dispatch new events, integrates the notification mechanism to the task in order to terminate or to execute the event concurrently with the task code, and executes control object procedures in order to allow initialization and okay, on every release and job completion, all the control objects are execute a procedure in order to allow these control objects to program temporal handlers, to cancel temporal events, or to directly dispatch the associated events with these control objects. And finally, the real-time task has been simplified because, as said before, all real-time task has hard code, the code to be executed on each event in this kind of structure, and right now you just simply perform the dispatch of the event, and the event knows what to do. So this code is simplified in the new version. So we have here control flow of a task split. This is the initialization. You perform the initialization of all the stuff. This is a release mechanism and the control object. When the job is released, before the job is released, okay, you execute on a release procedure of the control object that sets the timing event handler, and then starts to execute the task code. After a given amount of time, the handler, the time triggers and calls the event handler. This calls the release mechanism trigger event procedure in order to trigger the task split event, as it's an event that does not require to terminate the task, just directly dispatch that event, and the code of the event said, okay, there are this time to adjust job attributes, so execute adjust job attributes concurrently with the task code, and in this point the CPU change the task code, the task changed from one CPU to another. Okay, and finally, an introduction to the real-time code generation. Okay, all that stuff is more complex from the point of view of initialization code, because there are more components to be composed. So the idea is to use a scheduling code generator that builds a number of packages to support real-time scheduling for a given application, on top of the real-time utilities. And after that, they define real-time tasks, use this generated code, only implementing in that user-defined real-time task the functional code. The idea is that the task scheduling component and task attributes are fully implemented from this generation tool that uses the input from the time system requirements and the analysis results. Current prototype is implemented in the PHP, and as Mart specification is quite complex, we use a simple system description language. Okay, this is an example of this kind of specification, and the tool takes this information, deadline, period, type of task, attribute controller, worst case execution time, priority CPU, and all stuff, and the rest of the stuff, in order to generate all the scheduling code and to initialize everything, including the system policies and dispatching domains, and so on. So, conclusions. So we analyze the scheduling approaches in multiprocessor and take a look to the new requirements in order to be incorporated to real-time utilities, and extend these real-time utilities in order to support multiprocessor scheduling, to support element-based scheduling and complex tasks, and to allow model-driven engineering and code generation tools to generate the scheduling code. The good news is that the proposed design can be easily extended at library. These real-time utilities can be extended at the real-time level, or at the real-time utilities level, or also the application can add new events or new task types that can be required. And right now, the future work is that we are working on adapt these real-time utilities to multi-mode real-time application and mode changes. And that's all. Thank you.